Okay. Showing the beautiful curve of the gate with the side seal, extrusion, coming across.
Yeah. Well, down a little bit.
We're going to turn it up on the side. Now the gate is in the hole. Here we can see we're filling up the forebay for an overshot mode, and the gate perfectly sealing the entire backload of the water. What's that?
You want to come on up?
Oh, yeah. Wow, there's our seal. Isn't that
come through the wall, all 7 of them, and 1 for every foot under the gate itself, and it goes over to this manometer board over here. Now, if we're doing weir flow, because there's an undershot, the weir's here and there's an undershot here, the impact hit actually causes the reading over here to be a 1/100th of a foot higher than it is the rest of the way across. And it kind of tapers down this way very gradually, but only, quarter of it, less than a quarter of an inch across to the weir face itself. This is near the weir face. And then, but in the undershot flow, the water goes the other way as the water speeds up and changes from pressure to velocity energy. If you add all these up, the energies would probably be similar until it gets to the vena contracta, and then it comes back up again. This depicts the vena contracta, as we call it. That's the smallest area through a jet. The jet, after it exits the jet, it continuously gets smaller, and then it enlarges again.
And what is this stilling well here?
And this stilling well is just an amplification of tube number 7, which gives us a damped reading, a more precise reading with a point gauge of tube 7. It's actually teed into tube 7. Yes, our comparison measurement for the gauge is being made with a calibrated broad-crested weir. It's actually a long-throated flume of the that's been well published. we sense the depth here at the wall gauge. We can either manually read the wall gauge, which is pretty crude because it's pretty bouncy, or see these little holes in this pipe underwater there. There's 3 of them you can see, 6 of them you can see, and they're all the way around it. That pressure from that goes through the big pipe and out the back end and around to a stilling well with a precision point gauge in that stilling well. The accuracy on the flume is on the order of plus or minus 2% or better. And we can measure a range from about pretty small flows to very large flows.
Can you come with me as I'm going to...
Okay. And I'll show you the point on the... Everything is referenced on a flume from a point approximately where this stick is, right here. This is the sweet spot, you might say. It's about 1/3 to 1/4 the way through over the crest, and it's in the center line. If there's any anomalies like slight slopes in any direction, then this cancels out most of those. The stilling well is around, we put through this pipe down here, it goes through a small tube. You'll see the stilling well is going to be around here on the bottom back side. This is our 6-inch stilling well. We have a vernier reading point gauge on it. Actually, I'm using a hook gauge in this particular well. It's a little easier to see and a little more, I can detect about easily 1/1000th of a foot.
Wonderful. Jack,
The inflowing water to our head pool here. We now control the head pool through this gate, this small gate at this point. We open it to allow it to go into our steady system. Now let's go back and look at the head pool and how it operates. We have over here a skimming weir that helps us keep a constant head in this head pool, a constant depth in the head pool. Also, when that gets too deep, we have another radial gate that we can escape some water past it, so that we're still skimming some to keep a constant level in this head pool. Again, you see the upstream side of the control gate that actually goes into our test flume. You see the test flume down here. We have some baffling in this section to try to keep the water somewhat under control. That's sort of a nebulous thing, but we control many of the waves going down here. We've got them so that they're within reason approaching the gate for our study. I'm going to pass in front of you now.
okay.
And depths, we can read the depths here. They're just relative depths. We have to process them with to get the actual flow on the upstream device here. We'll move down here, and we have a series of restrictions so that we can cause submergence on the gate. So these are submerged flow characteristics of the gate at the present time. And this is just kind of a jammed up thing. Most anything to work to cross the back water. Then here is gate again, and we did have a wave buffer here, but it's fallen down. We have to raise it back up. It's basically a box that supposed to help control the flow to the flume to make it a little more level. And the flume actually is not read off that gauge. It's feeding about 30 cubic feet per second now, but that's just a rough flow. The actual flow is measured through small holes in the bottom of the flume under the gauge. We go out to a large stilling well, and a point gauge averages them down nicely. Down here with the point gauge is where the actual depth above the flume is read, and it takes all the randomness out of those waves. The torque on this gate, the force to open it, and we'll convert that force to torque.
And what is this tool here?
I'm going to measure the force at this distance from the center to open it. And of course, force times distance is torque, and we'll have a torque number there.
Okay. Okay, we need to calibrate the torque on the gate. So we're using this crane here to pull up on a dynamometer on the gate. All right, here we have the control panel for the gate, where we have a PLC and other pieces of equipment. And our electrician, Robin, is going to define all of the elements. Robin, please start with the PLC.
Okay, this is the SCADA Pack Plus. This will take all the information from the level sensors upstream and downstream, any temperature sensors that you may want to add later on. Currently, upstream and downstream levels are the only ones that are coming back as an analog signal. On the discrete inputs in this row is a binary representation of the encoder position on the main shaft for the gate. Information in the PLC can be displayed on the operator interface terminal on the sub-panel face. We will see upstream and downstream levels. We will have set points for upstream and downstream levels, and we will also be able to show the angle of the main shaft for the gate. The end devices for the real world is an absolute encoder by Allen Bradley. As the shaft rotates, it changes the decimal value by setting or clearing bits that are coming into the discrete input terminal for the SCADA pack itself. We will have 32,767 counts for a 360-degree rotation for the shaft. We don't anticipate anything greater than 120 degrees of rotation, so we have very good resolution using this encoder. Upstream and downstream level transmitters are Miltronic devices. They are ultrasonic, and you can see as I lower the device, bring it closer to the floor, we will see the value of the level decrease.
What does that value represent?
That is actually in feet, and decimals
of a foot.
portions thereof.
And we'll use two of those.
Yes, and I've got them labeled as to downstream
That's great.
and upstream, in addition to where the cord comes into the panel here. This is the upstream level transmitter, downstream level transmitter. This is the cable for the encoder, and this is going to be the entrance for the command for the limit torque to open or close the gate.
Excellent. What are the other devices inside the...
This is the 24-volt power supply here. It brings in 120 volts from the cord right here that can be plugged into a standard outlet.
Okay.
Changes the 120 volts to 24 volts, which everything else operates on is low voltage.
Okay. Where's it coming from the far end up?
Okay, this is the 5 amp breaker for the 120 volt supply coming in. This is the neutral.
Okay.
The black terminals here are all common. They've got a jumper bar here, so this is the wire for the 24 volt negative from the power supply. We've got a barrier here, and we've got all of the fuses for the 24 volt supply to any external devices. The red wire here is coming from the 24 volt power supply. It is the positive lead. Again, we have jumper comb in here, so the supply to the top of the fuses is all from the same location. And each one of the fuses, and we are currently using 5, are 1 amp fuses going out to each one of the devices.
Okay. What is this block now?
This block is all of the real world devices coming back in, with the exception of the encoder. Because there were so many conductors for the encoder, we're using a 14-bit resolution, that it was much better to bring the cable directly through the panduit and sweep up into the bottom of the discrete input. The first two positions here are the upstream and the downstream level transmitters. Those wires come up here. It's just a signal. So those wires come up here. They're routed through the panduit, and then they come up here to analog input channel 0 and channel 1.
Great.
The supply for the power, because they are a loop powered device, comes from the fuses here. If we look in order, everything that is fused on the 24 volt here is the SCADA pack 24 volt, the operator interface terminal 24 volt, upstream level transmitter, downstream level transmitter, and then lastly the 24 volt that is supplied to the encoder.
Okay.
Everything follows the same thing here. If you need a 24 volt negative or return path for that, it goes SCADA pack, OIT. This one is the common for the discrete inputs on the SCADA pack.
All right.
And then the last one, the small gauge wire, is the negative 24 volts again going to the encoder.
What is the pulse encoder then versus a 420 milliamp? Is that something we should talk about?
Pulse encoder will basically indicate a rate of speed, and you can use a processor to indicate the number of revolutions that a shaft on the encoder has made, so you would get a totalization effect.
All right.
The advantage behind the absolute encoder is we will always know the exact position of the main shaft on the gate.
Could you show us a little bit about the maple and the buttons there?
Sure.
Okay. Let me sort of get back on the ladder here. All righty.
Right now we just have 4 screens.
All right.
You'll notice in the screen here that there is an arrow, right and left arrow key. What I did was I chained all of the screens together, so if you want to scroll through, all you have to do is hit the page down button.
All right.
So in this screen we show the calculated flow in cubic feet per second, and we show the value for a set point. If I go to the next screen, it would indicate the upstream and downstream level. This one shows the upstream and downstream set points for the level control. And then the very last screen does show the gate angle. Now, if for some reason we want to change a set point, and in this case I'm going to change the set point for the flow rate. You'll see that there is a cursor underneath the 25 indicating that that is a read-write field. So the first thing you want to do is actually hit the clear button. At that point it will eliminate that value. There is a number keypad here, so what we previously had is a value of 25. Now I'm going to hit a 3 and a 0 and then hit the enter key. Now it shows you that, and this actually is a number that the processor, the PLC, is using now, is it's going to strive for the 30 cubic feet per second flow rate.
And then this will eventually, when it's all set up, change the angle of the gate by turning the motor on and off.
Yes.
And going through the gearbox.
And depending if the flow rate is calculated as being higher than the 30 cubic feet per second, the command will be to close the gate.
Okay.
If it is less than the 30 cubic feet per second, it will issue a command to open the gate.
Right. Can you close the box? And we can see what this looks like. Oh, wow. What a nice panel.
Sealed against the environment.
Is this NEMA 4?
Yes, it is.
Oh, great. All right. I'll take a